Welcome back. We now want to talk about parameter learning in neural networks. And as we have seen is that a neural network is more or less, simply speaking, a very complicated parametric function with multiple, many parameters in practice, which we have to derive in some way. So how do we do this? Right? We set up the loss function beside the actual model. And then, not surprisingly, we are often using gradient descent to find a good solution for these parameters W. So the issue is that this loss function and then with this model included, right, so to say, is often not convex, right? So here this E illustrates the loss, including the neural network, right? This is often a non-convex function, as you can imagine, unlike, for example, to a standard logistic regression model. So indeed, optimization is usually very tricky. And you have seen this already, and you had this discussion, the optimization part. If it's non-convex, it means there might be multiple local minima, which we can stuck with, right? As also shown here in this figure, right? We have here potentially multiple local minima. So there might not be the hope that we can really find the global optimum. So indeed, what we can do is then, or what we do often in practice is, for example, to just do multiple restarts, for example, or that we hope that all these modern optimizers like Adam and so on and so forth, that they lead to a good solution at least. Okay, but in principle, indeed, what we are doing usually is when we want to do learning in neural network, we just do the standard, as you know it, gradient descent update. Old parameter vectors, we take the gradient, negative direction of the gradient to a specific step size, then reduce from the old parameters, and this gives us the new ones. Okay, so that's the full principle, usually at least for neural networks, which we have to use, with the caveats you should please keep in mind, which can happen here. So what is a problem now, right? So in principle, you know all this, right? You know how gradient descent works, so we just have to compute the gradient here, right? And that's it. We just have to compute the gradient. However, indeed, this is not really now just have to compute, because the full point of this neural network was that we have a rather complicated, deep function with all these different kind of transformations. And indeed, computing this gradient, as you might have done it for logistic regression by hand, is indeed not really a choice for neural networks, right? So manually working out this gradient of our model, right? And then even implementing it potentially, right, in a computer is extremely cumbersome and even tricky, right? It might be complicated gradients and so on and so forth. So you don't want to do this, right? Because even for logistic regression, it was somehow like a pain. If you can imagine, if it's a complicated model and then you add something, you have to derive it again by hand. So this is really not how you want to do it. This doesn't really work. There are some other points which we also see later in a couple of seconds. So the solution by hand is for sure not a solution. You can think about doing some kind of numeric computation of the gradient, some approximation of the gradient. I guess this is how you also learn gradients in potentially in high school. So what we mean by this is, for example, you can of course say, okay, I have the current parameters and I sample some epsilon, so to say, around it, right? I'm looking at the neighborhood, right? And then you know the definition of a gradient is exactly this, right? It's current point, some epsilon away, and then divided by this epsilon, right? You can do this. You can do this numerically by sampling, so to say, multiple different epsilons, right? And then you get a numerical approximation of your gradient. So the issue is, and this is why it doesn't really work for neural networks, is that the evaluation of this quantity here, right, computing the gradient with respect to this parameter, requires O of number parameters operations. Why? Because you see that you have to evaluate here your function, right? So this E of W is the loss you have at the moment, right? It means you have to take your input, you have to put it through your neural network with the current weights, right? So input X and weights W, you put it through your neural network, you get a prediction, you compute the loss. So this is what this term means here, right? So evaluating this or this part means always evaluating your full neural network, O of W. And as you can imagine, this is extremely important, expensive, because your neural network might be rather big. And of course, you don't just need this here for one W, but you need it for all parameters, which again means you have some O of W complexity. Okay, so for every parameter, W many, you have to evaluate your network, meaning W many operations, which at the end of the day means you have squared in the parameter operations you have to do. So extremely expensive to get a gradient. And as you know, you have to do multiple gradient steps to find a solution, right? So this is how gradient descent works. So this is extremely expensive and also not the most accurate, right? Because numerical approximation of the gradient might not be very stable, for example. So this is also not a choice. Numeric is not a choice. By hand is not a choice. So what can we do? You can think about, okay, let's do symbolic differentiation. So what does symbolic differentiation mean? It means that we automate the process of deriving the gradient, which you learned in high school, by a computer, right? So you know, for example, if the function is x squared, that the gradient is 2 times x, for example, right? And since a neural network is also just some function, right? Of course, it's more complicated than x squared, but it's some function. You can think about automating this differentiation. And indeed, there are tools for this. You can derive symbolically the gradient of complicated functions automatically, okay? So in principle, you can do this, right? So you have your network function, your f function, or this e of w function, including the loss, right? So again, e of w could be something like this. Let me just add it. So it could be like the prediction y minus the neural network output squared over all instances I, right? Just to be clear here, one more time. So here's the neural network part, here's your loss part, and this is what this function is, right? So you can do this. You can automatically compute the gradient, symbolically compute the gradient of this, but even writing down this gradient might be extremely expensive, okay? Why? Because on one hand, you might have exponentially many different cases in this kind of gradient, right? It's not as simple as you have x squared and then the gradient is 2 times x, but you have, for example, this Rayleigh activation function we have seen on some slides, right? So the Rayleigh was like this, right? If your data, so here was the 0 line, so you have the input here and you have the output here of the Rayleigh. If the input is negative, the Rayleigh is 0. If the input is positive, the Rayleigh is just forwarding it, so to say. You see you have here a case distinction, right? So the output of the Rayleigh is either 0 or the number you have fed in. So it's a case. And now you think about if you have an arbitrary neural network, we have multiple of these Rayleighs, right? There are exponentially many different cases, right? So if you have like a neural network, right, you have here a tiny neural network, let's say, right, and let's say we are using here Rayleighs, then for example this neuron, right, so this is, I guess I didn't use this term yet, so this is called a neuron, right, this neuron can either be on the negative side or on the positive side. So 2 cases. This neuron can either be on the negative side or on the positive side, right, and here as well. And you see that, of course, since these neurons have different kind of choices or cases, right? Of course, also the gradient looks different. So either the gradient is 0 or the gradient is 1. Gradient 0 or 1, gradient 0 or 1, gradient 0 or 1, for example, right? So you see that in general, then, of course, the gradient of the full function has exponentially many different cases because we have all these different combinations which can kick in, so to say, okay? So again, writing down symbolically the gradient doesn't work, right? It might be too big to write down even. And then there's a second point is, actually, when you would write down this gradient, right, in all these different possible cases, you see that many, many terms reappear, right? So you can have this gradient function, and simply speaking, the gradient function, for example, you have multiple times the term x squared, let's say, right? It appears in multiple times, right? Because you see that, for example, this neuron here, if you make it larger, for example, this neuron might be used in multiple, let's say we have multiple layers, right? Let's say we have more layers here. So here, for example, you see that this neuron here plays a role for many other neurons as well, right? So the gradient of this one plays also a role in multiple different pieces, right? And this reappearing of different gradient computations is also not possible if you just naively write down symbolically your gradient, right? You don't see that some calculations appear multiple times, and then of course you don't use this information. You have to recalculate it again and again. Again, simply speaking, if you have the term x squared multiple times here, right? Because here this has an x squared in this part and has an x squared in this part, then you don't exploit this fact, and this is just inefficient. Okay? So this point, by the way, also holds, or actually both terms points hold also when you derive the gradient by hand, right? You might get a very large function, and you might not use the reappearing aspect that terms appear multiple times, because this f is hierarchically constructed. So the neural network is a hierarchy which reuses different informations. So what is then the solution? Symbolic is not the solution. Numerical is not the solution. By hand for sure is also not the solution, because by hand means simply symbolic by hand, right? Indeed, the solution is automatic differentiation, and specifically for neural networks, it's called backpropagation. Okay. So what is the core point here of this backpropagation, or this automatic differentiation? The core point is indeed, or one core point is, that actually you don't need the full gradient, right? You're not really interested in writing down the gradient of your full neural network. That's not the point. What you only need is, you need the gradient at the current point when you're doing gradient descent, right? So that was the full point of gradient descent. You have a current solution, and you update this solution. So indeed, it is enough to get this gradient at the current position. You don't care about all the other positions, all the other solutions, right? You don't care about that, all the different combinations, whether the ReLU is activated or non-activated, right? Whether it's deactivated, meaning 0, or activated, whether it's positive, right? You only care about the current solution. And this, of course, is only one, right? Because at the moment, when you have a specific parameter solution, you know which ReLUs are on the positive side and which ReLUs, for example, on the negative side. And then, of course, you can compute this gradient at this position more efficiently, okay? And indeed, this is what we will explain later in detail. We want to use backpropagation because it evaluates the gradient at the current position, and then it only requires O to the W complexity, meaning more or less like a constant number of passes through your neural network. Okay. Indeed, every of these neurons, and here you see the word again, right? The neurons are these kind of elements in your neural network, is indeed only visited twice in backpropagation. So a constant number of times, and not like in quadratic or even exponentially blow up, but really just you have to go twice through your neural network to compute the gradient at the current position. So that's the way to go. And indeed, let me just repeat it one more time. I guess that's very important to remember, that we need here an efficient way of computing the gradients, because neural networks can become very large, right? They are very deep networks with very complicated operations, and we need some efficient ways of computing this gradient, because otherwise this training does not work at all. So how does now backpropagation work? How can we compute the gradient at the current position in an efficient way? And I want to show you here with some example to make this principle, I guess, very clear. So let's say we have a very simple function, f of x, right? So x is the input, so to say, to our neural network, and our neural network is, again, it's just a toy example, applying these kind of operations, okay? And here let's even say we don't care about like some parametric form. This is just some deterministic fixed function, okay? But of course you can imagine that this is much more complicated, where we have other kinds of parameters and so on and so forth involved. So we have this function f of x, right? And you see, again, similar to a neural network, this is just a hierarchical composition we are applying, right? We start with our input x, we apply some function a of x. What is a of x? Here a of x is minus x, as you see it here. Then we apply the next function, b, right? We apply b to the output of the previous function, right? So b of a, so to say, right? So we have here, this is our a, this is the output of the previous layer. We feed it into the next layer. We apply b, which is here, for example, x of it, right? Then we apply the function c, which is here, for example, applying the sinus, right? So sine of b, and so on and so forth. And the last layer, so to say, is this operation 2 divided by whatever was the output here, okay? So you see this toy example is indeed somehow like a neural network, right? We have the input, and then we have the chain of operations, right? The input goes to some function, which gives you some output, and this output becomes the input of the next layer, right? Applying some function, and then it becomes the output becomes the input of the next layer, and so on and so forth. So you see it here, this chain. So often what we are doing, what you will see in these modern deep learning frameworks or machine learning frameworks in general, is that you can represent this function as a computational graph. Okay, a computational graph is just a chain, so to say, how you apply these functions. You start from the input, okay, and then you, so to say, forward this input to the next function, often called a module, which is here this function a, which is minus x. Okay, and this minus x is then here the output, right, which is forwarded to the next module, to the function b, and b applies x to what it receives. Okay, it gets some output, and this output becomes the input for the next function, and so on and so forth, right? So here you see input, and here are the functions we are applying. Okay, so it looks here slightly different to this illustration we had at the very beginning. Okay, at the very beginning we had these neural networks where we had the weights at the edges, right? This is one default representation. Please don't confuse it here at the moment, right? Here you see that we have here the functions are at the nodes. Okay, so there are no weights or whatsoever at the edges. So here the functions are the specific nodes. It's a slightly different illustration. Please don't confuse these two. Okay. So here this shows you the chain, right? The chain of how we construct our function. At the end of the day, this is the output d, right? Because d is the last transformation we are doing. Good. So now the question we want to answer is, how can we compute the derivative of this function based on this computational graph in an efficient way at a specific position? And for this, let's first look at it from a general perspective again. So how can we get the gradient of this output, right? So f is here our final function, right? How can we get this at the specific x position, so to say? And the core point, and this is one fundamental aspect, one of the fundamental aspects of regression, is that we can, of course, apply the so-called chain rule, right? Chain rule you learned in high school, I guess. So getting the gradient of f with respect to x means, if you look at this decomposition, we can compute the gradient of d, right? D equals to f here in this case, right? So d is f. We can take the gradient of d with respect to c, right? Then of c with respect to b, b with respect to a with respect to x. So indeed, if you have this kind of representation of the gradient, right, with these derivatives here, then you can indeed look at the chain rule really as that you can cancel out these terms, right? You can cancel out, as you learn it from standard fractions, so to say, all these terms, and you'll see what is left is d with respect to x, while d is already f, right? D and f has the same output, okay? So this is a chain rule. So we can use a chain rule. So how can we then get our derivative? So how can we get the global derivative? So f with respect to x, we can get it by computing these so-called local derivatives. So once we have all these different pieces, right, we can just multiply them and then we get the global derivative, right? Because that's simply the chain rule. Okay. So the question is now, however, right, how can we find these local derivatives in a somehow efficient way, for example, right? Because once we have them, we can get the global derivative we are interested in. Okay, so how does it work then for backpropagation? Or let's say this is like not the final version of backpropagation. I'll show you later on how it's actually done, but this is somewhat like the intuitive idea of backpropagation. Okay, so first what you do in backpropagation is you write down these so-called modules. These are the small pieces, so to say, the small functions you're applying. Okay, so what modules you are using is up to you, right? So here again, in this case, the modules were just some simple functions like applying the exp or doing the minus of the input. Okay, so module always, however, is like you have an input, some transformation, then the output. Okay, so you write down the modules. Then what you do is you derive the local derivatives symbolically. Okay, so you find somehow like an estimate for not an estimate, and derivation symbolically of these local derivatives, b to a to x, d to c. Okay, we do this in an example later. So you do this symbolically. Then you do a so-called forward pass to your network, meaning you have your current specific input, x, right? You have your current setting, right? The current parameter solution. You do a so-called forward pass to compute this function f of x, to compute your output. And what you do is you remember the intermediate values. So you not only compute f of x, but you also store all these intermediate values. You store minus x, you store x of a, right, which is x of minus x. You store this here, you store this here, you store all these intermediate steps. Then you compute the local derivatives, right? And once you have the local derivatives, you can multiply them, and then you get your global derivative, okay? So indeed, these steps. Define the modules, compute the local derivatives of these modules symbolically, do a so-called forward pass. I'll show you what this means to get these values for a specific current solution. And then once you have the specific current solution, you can also compute the local derivatives now for this current specific solution you have at the hand. And then once you multiply this, you get your global derivative. So these are essentially the steps. So let's look at this. So set up the modules we did, right? So we have here defined our modules. These are the modules we want to use. And once we chain them up, we get our overall function. Okay, done. Second step, compute the local derivative symbolically. Okay, let's do this, right? That's super simple here, right? Because we have simple functions. What is the derivative or the local derivative of minus x? Of course, it's just minus 1, right? So a with respect to x is just minus 1. What is the derivative of this function, right? With respect to a, and that's a trick here, right? You're not interested here in the overall derivative b with respect to x, but you're interested in b with respect to a. And this again simple, right? B with respect to a, you know what the gradient of e of a is. It's again just e of a, right? Same here. Sine becomes a cosine. 2 divided by c becomes minus 2 divided by c squared. Okay, so you see these modules are usually very simple functions, even later on in a neural network setting. And then deriving these local derivatives symbolically is extremely simple. Okay, and what is important also to notice, these local derivatives here, right, they really just link to the modules, right, to the individual modules. So this can be computed just via the information of the module. It doesn't matter what happens here, right? To compute this derivative of d, it's really just the input here, which we called here c, right? And then we can compute the derivative symbolically, right? It doesn't matter what this other part or even what this part is here, right? It can be done independently per module. You have this module, which is the function, and then you have also the corresponding symbolic local derivative, okay? So now comes the question, right? How do we get the global derivative? And we first have to do this by doing a forward pass through our computation graph, okay? The computation graph, again, we want to evaluate only at a specific point. So let's say we want to compute the solution at the point minus 4.4999, right? This is just some example, right? So at the end of the day, we want to know the gradient at this position, okay? So one side remark that you're not confused. So here we call it x because we talk about the general function. Later on, of course, we're interested in the gradient with respect to the parameters, what we want to learn, right? So later on we have a gradient with respect to w, but since here we have general function, we just call it x, right? So in your head, you can already replace x by w, but it doesn't matter how you call this, right? It's just some variable where we want to take the gradient at, so to say, okay? So this is what we want to do at this point. So what do? We do this forward pass first to get our intermediate values of all these different functions we are applying. What does it mean? Right? X is minus 4 point whatever. So A, of course, is then plus 4 point because this was the operation. B becomes 90, right? We apply E to A to this value. And then C becomes 1 because it's a sine of 90. And then D becomes 2, of course. Okay? So this is really just applying the functions, right? This is called the forward pass because you have your input and it's pushed forward through your network and you have all the corresponding intermediate outputs gathered, okay? So what we have seen also previously in this neural network setting, so to say, you have computed all these intermediate representations, all these intermediate values, which you now in the next step need to compute your gradient, okay? So you have these. So given these values, right, what is the next step? We want to do the backward pass, sort of backward pass, where we compute now all these local derivatives at these points. Okay, so what were these local derivatives again? Right, it's d to c, c with respect to b, and so on and so forth. And now since we have computed these values, right, we know all these intermediate values, we can again just plug it in. Okay, so what do I mean with this? So we have seen that, for example, let's start here, that the local derivative of the module B with respect to the parameter A was just x of A, right? So this is the local derivative. And now what is A? Yeah, we just computed it here, right? So here A is 4.499. So we plug it in, we get 90. And same here, for example. What was the local derivative of D with respect to C? What was it? It was minus 2 divided by C squared, right? Some simple function. Wait a second, we now have our C, right? Our C was apparently 2, so we just plug it in, we get minus 1/2, right? Here the same, again, C with respect to B was cosine of B, right? Again, this is a local derivative. Oh, wait a second, we know what B is, right? B was apparently 90, right? So what do we get? 0. Okay. So here, just to conclude this, right, the local derivative of A with respect to X was minus 1. So there is no unknown, so to say, right? So it's immediately minus 1. Okay, so we have now computed these values for this local derivative at the current point. Okay, so you see it here, what we did first in the first step, we computed in the forward pass these intermediate values. And now in a backward pass, we can go back and plug in, so to say, our solutions to get also the local derivatives, right? We get here, where is it? Here the D, we get here the minus 1/2. Then we go here, we get the 0. We go here, we get the 90. We go here, we get the minus 1. Okay. And this is what we do here, right? This is how we get the overall gradient, right? Again, this is what we're interested in. We want to have the gradient of our loss function, let's say, with respect to the parameters, which we call x here. Chain rule, right? That's equivalent. And now we have all these different pieces, right? Here are the numbers. We just multiply it and we get our final result, which is here 0 in this case. Okay. So again, very simple setting, right? Once you have the local derivatives for every of your module, right? You have the local derivatives of your module, you can do a forward pass to get the intermediate, all these intermediate values, right? All these variables you get, so to say, values for. Right, and then you can go backward to plug it in into your local derivative, so to say, right? Then you get also actual values for your local derivatives, which you can just sum up, and then you get your global derivative. Okay? So that's a big picture. There are some more tricks later on. Okay, so in general, of course, the function is not just a simple chain, right? Where we just have one input and then we just forward it and we get to the end, right? It can look more complicated. So for example, our function can have multiple inputs, which we usually have, right? Because we do not just have one scalar in, but we have like even a vector in, or we have an image in, which has like, I don't know, 1 million pixels, for example. So in general, your modules can have multiple inputs, right? Again, think about these kind of as modules, right? So here, for example, we have X and Y as features, right? Then we have a module A and a module B applied to it. And then we have another module C, which here, right, that's the important part, has now 2 different inputs, okay? So what does this mean? So at the end of the day, for example, we want to compute the derivative of the final function, the final output C, for example, with respect to X, right? Again, think about that these are now 2 different parameters, let's say, right? So this is parameter 1 and this is parameter 2, for example, right? We want to know what is the gradient of C with respect to X and with respect to Y, for example, okay? So how can we do this? I mean, it's actually very simple. You can essentially compute the derivative along each of these paths here, right? You see that this is simply chain rule again, C with respect to A with respect to X along this path. Or here, C with respect to B and then B with respect to Y. And then again, you can do exactly the same as before, right? You do a forward pass, compute all these intermediate variables. So compute C, compute A, compute X. X you have usually, compute C, B, and Y, right? Evaluate the local gradient, and you get your final gradients by multiplying them up, right? So it's exactly the same. You just have to derive the derivative, so to say, along these paths. So of course the paths, by the way, they can have also like, they can essentially split and join together, right? So here you have more like some kind of a DAG, or you have one unique path which is going to this function, right? But of course it can also look like this, right? What is the difference? The difference is now that this x, of course, plays a role in C in two paths, so to say, right? So the x plays a role in A and then in C and then over B. So x indirectly plays a role, so to say, via two different functions, two different models, right? So this is also how your function can look like, okay? So what is then the solution, right? In this case, you have to take the sum of the derivative along this path. Or simply speaking, again, if you're interested in C with respect to x, right? So what is the result of this, right? It's C with respect to A and A with respect to x, and then plus C with respect to B, B with respect to x, right? It's just the sum along these different derivatives, okay? And in general, if it looks like this, for example, right, so you have specific input x, you have multiple different functions which are all absorbing x in some or the other way, and they are all going at the same time to C. It's really just what we have written here. It's in general the sum over these different modules only. Okay, you see again, you have the sum over these different inputs, so to say. Right here, it's the sum, all these different local gradients C with respect to AI, and then you have AI with respect to x. Okay, so this is simply the multivariate chain rule, so to say. Right? In general, you know the chain rule, which we have shown on the previous slide, which is really like a chain, so to say, in the so-called computational graph. In general, you can have a so-called multivariate chain rule, which looks like this here. Okay, the gradient of C with respect to x is a bit more complicated. It's like the sum along all these different kind of paths here. Okay, but it's still extremely simple. Okay, in general, and this is now what we want to quickly talk about, that you get a feeling from a technical side is, in general, we talk often about Jacobians and gradients in these models. And you have seen this actually already a lot in the programming exercises we have handed out, because one core principle of all these modern frameworks is that you can vectorize, or that you can represent your data in some kind of a matrix, vector or tensor form, right? And for one reason, that you don't want to do for loops, right? So to speed up your calculation. But this is also then important here if you're looking at the calculation for the gradient, because often you don't want to do it in a very naive scalar way, but you do it in a vectorized, in a matrix kind of way. And for this, it's important to know some concepts, specifically the Jacobian, because I assume that the gradient you are aware of. So what we see in general here as these modules, right, as these kind of modules here, in general, these are functions which can get n inputs and produce m outputs. Okay, so every module is really just a function which receives a couple of inputs and outputs also a couple of values, right? And this does not be restricted to scalar outputs or scalar inputs like here, but in general, we can have multiple inputs and multiple outputs. Okay, so like here, for example, we have multiple outgoing, and here we have multiple ingoing. So in general, we have such kind of functions. So you can really think about, you have some vector in and some vector out. Okay, and what is a notion you should be aware of is the so-called Jacobian. The Jacobian is, simply speaking, all the different possibilities of taking these partial derivatives. So partial derivative means you take a specific output, so for example output 1, right? Remember, we have m many outputs, and you compute the derivative of output 1 with respect to input 1, for example, which is here this position. Or you compute the output, the derivative of output 1 with respect to input n, okay? Or the derivative of output m with respect to input 1, okay? And so on and so forth, all the different combinations. You see specific input, right, 1 to m, and specific input 1 to n. Okay, so the Jacobian is simply the matrix m times n, which contains all these partial derivatives. So you can think about that this is like the gradient, so to say, if you're operating on functions with n and m in and outputs. Okay, so this is the Jacobian if you represent this in this kind of vectorized form. Okay. So what you usually what we usually call as a gradient, means then simply speaking that we have a function which has n inputs and a scalar output, right? So let's say the loss is the output. And what we are usually computing is then the gradient of such functions, right? We had like a loss function which has a scalar output, and we were computing the gradient, okay? So meaning we have here our loss, which is a scalar, and we computed the gradient. As you know, the gradient then of such a function, of course, is a vector, right? The gradient is a vector, an n-dimensional column vector, and it corresponds to, yeah, as you know, the gradient with respect to all these m parameters here, okay? So linking it to this Jacobian we have just introduced, the Jacobian is simply the transpose, or let me write differently, the gradient is simply the transpose of the Jacobian, right? So please be careful with this, and because we have here somehow like changed the order, right? You see that here this is the input, the output and the input, right? So output and input, right? While, so meaning if we have like a scalar output, this would be a 1 times m matrix, right? Scalar output means we just have this this row here, right? So this row here. So the transpose of it, meaning the column vector, would be the usual gradient we are computing, okay? So here it's again written. So the gradient, which we have usually indicated here with this triangle sign, so to say, right? The gradient sign in our notation is a transpose of the Jacobian, okay? Where we have here these partial derivatives, okay? So this is just a notion where you have to be a bit careful with, right? So the gradient, usually indicated with this sign in our lecture, corresponds to the transpose of the Jacobian, where the Jacobian is the most general form, so to say, because it can handle multiple inputs and multiple outputs. Okay. One last point. Note also that the gradient, of course, has the same shape as the input to the function, right? So here, the scalar, this vector here, like a 5-dimensional column vector, this here has the same shape, same dimensionality as the gradient, right? While the again the Jacobian for this function would be like transposed. Okay. So the Jacobian, right? Why did I introduce here the Jacobian and this notation, right? It's important because at the end of the day, again, the functions, the modules we are looking at, they are arbitrary functions with n inputs and m outputs, okay? And when we want to compute the derivative at the end of the day, as you can imagine, it's not only the gradient we need, but it's actually the Jacobian we need because the functions are arbitrary functions, okay? Good, so this was just definition. Please don't confuse this. And now we do this here in this matrix form, right? So what we have seen before was this chain rule, or this multivariate chain rule, let's say, even. And now we can represent this also in a matrix form using this Jacobian. So let's look at an example. So let's say we have a function c, which here is now a scalar again, right? Let's say our loss function, which produces a scalar. And we want to know what is the derivative with respect to some variable xj, right? So in general, and what we have seen before is like we can apply this multivariate chain rule, if you want to call it in such a way, by computing first the derivative of c with respect to a1, and then a1 with respect to xj, and then we sum it up, okay? So this is what we have seen before, right? So all these kind of partial local derivatives, right, and summed up. Now, since we have the notion of the Jacobian, right, which collects all these partial derivatives together in one big matrix, we can indeed also write it more compactly in this way. We have here our function we're interested in. We take we want to compute the derivative with every possible x, right? Because we do not just have one x, we have multiple x, we have multiple parameters, right? This can equivalently written as the Jacobian of c with respect to a and the Jacobian of a with respect to x, right? Or not with respect, but it's the Jacobian of this function, right? It's the Jacobian of a and it's the Jacobian of c corresponding to the specific input, okay? Where again, we have used here this notation from before, right? How our Jacobian is set up. Or simply speaking, if we want to do it for a scalar output, where it means we have like the gradient, right? The gradient of our function c with respect to some parameter x, right? If we have this kind of general form, right, is the transpose of the Jacobian of a with respect to x here and the gradient of c with respect to a, okay? So you just have to be now careful with the corresponding signs, okay? That the signs match here, that you can multiply, right? Because this here is a vector, and this here is some other form we will talk about in a second. Okay, this here is in general a matrix. Okay, because it's a general Jacobian. Okay, good. So why do we do this? We do this because inside these frameworks we often have this kind of vectorized or matricized form, right? And we don't usually operate here on this kind of scalar form, which is somehow tedious because then you have all these different kind of sums. But indeed, you can just write it more compactly in a specific matrix or vector form. Okay. Please don't be confused. I know this is now lots of like playing around with like matrix notation and so on and so forth. Important to remember is at the end of the day, it's really just again the chain rule, because you see that if you have the definition of a Jacobian, right, then this really looks like the standard chain rule we have seen before, which you know from standard high school, where you only operated on scalars, right? So from the form it looks exactly the same as before, but just be careful, these are no longer scalars, but these might be vectors or matrices or even tensors. So let's look at an example to make it less abstract then. So let's say we have a simple regression problem, right? Let's say we have some input x, right, d-dimension, and we have a scalar output y, which is continuous. So what can we do? We can use a specific neural network. Okay, what do we do? Let's say we do first our linear transformation, wx plus b. So this b is here now this bias. Here we don't have absorbed this constant 1, so we have an explicit bias term here. So here, this is the first linear transformation. We apply a nonlinearity, like a sigmoid, for example, right here. Then we have another layer, let's say, right? So we take here the output. This is a hidden representation, right? We take this hidden representation, we multiply it again, so some affine layer. We get another output, and since this is a regression, we don't apply another activation. We just treat this as our prediction, and we subtract it from the true target, square it, and this is our loss. Okay, so these are the different modules. Okay, so this is now a simple non-linear regression, right, where we have here our first input x, then we have here our, so like this, for example, right, scalar output, it looks like this. So we have here input x, here, so this is x, this is h, and this is y hat, so to say, what we are getting, right? Input x, hidden representation, and y, where be careful that we don't have any activation after the y because we're doing regression. And then we have the loss. So this is our neural network, right? A simple neural network, one hidden layer. And you can also now think about these different functions as our modules, right? The modules, how we stack together our function, right? We are applying so to say, e of y hat of h of a, so to say, right? These are the different modules. And what we are now interested in is, of course, we are interested in the gradient of our loss function with respect to our parameters w. Okay, so what I said before, of course, we're interested in the parameter and the gradient with respect to the parameters w. Okay, so this is what we want to compute. Okay, so this is what we want to compute. And you see already that these are now more complicated functions which have, for example, here multiple inputs and multiple outputs, right? It could be like, I don't know, 5 dimensions in and 5 dimensions out. Okay, so it's some arbitrary functions which are more complicated from before. And this is why we need this Jacobian in a second. But in general, we can do the same as we learned in this toy example for backpropagation. So what do we have to do? We first have to compute these local derivatives, so to say, right? Because we want to apply this chain rule. And again, now knowing this notion of the Jacobian, it looks as before, right? Here is our target. We are interested in computing the gradient at w. And here are all these local derivatives. Okay, local derivatives at all these different at all these different modules. And one local derivative, of course, is now, if you look at all these, for example, the local derivative of A with respect to W. Okay? And now, of course, is the question, what does this actually mean? Right? What does this mean to have here a function which has multiple inputs, and here we have even a matrix, right? Because W is also a matrix. What does it mean to compute the derivative of a vector A, right? Because this is also a vector with respect to a matrix W, right? So this is even more general than what we have seen before. And here you see a bit of this matrix calculus, which is for some of you might be a bit new, and probably you should then look again in this matrix cookbook, for example, or other resources. But in general, you can look at it in a very, let's say, abstract sense. So what do we have in general? And let's start very simple. Let's say you have some functions, right? You have functions which have a specific input and have a specific output, okay? And let's start with the easiest, which you learned in high school, I guess. You have functions which have a scalar in and a scalar out, right? So for example, f of x equals to x squared, where x is a scalar. And then you know the gradient is 2x, right? And you see specifically that then the derivative itself, or the Jacobian, if you want to, is also a scalar, right? Scalar in, scalar out, like f of x, like with a scalar, right? F of x equals to x squared, right? Then you know the gradient is 2x, so the gradient is also just a scalar, okay? If you, for example, and this is also easy, what you already know, if you have, let's say, a vector in and a scalar out, I don't know, let's say we take the norm of x, right? And you want to compute the gradient here in this case, right? Or the Jacobian in general, right? You have a vector in and a scalar out. What is a gradient? What is a Jacobian? It's again a vector, right? Why is it a vector? Because you're interested in how does the output change when you are changing every of these different inputs, right? So how does a change in one of the different inputs affects the output, right? This is what the gradient or what the Jacobian is measuring. And then, of course, the derivative of the Jacobian is itself a vector, right? Because we have here a vector, and we want to know how does it change in every of these components affect the output, right? This is why we have a vector. This tells us how does it change in all these different components affects the output. And the same here, if we have a matrix, right? Let's say we have a matrix. I don't know how to draw this now. Let's say we have a matrix, let's call it W. And here we are doing something which is like, let's say also some norm, for example. What do you want to know if you take the Jacobian of this? You want to know how does it change in any of these components, right? Which, let's say it's a 10 times 10 matrix. How does changing the first component affect the output? How does changing this next component change the output? How does changing one of these 10 times 10 positions changes the output, right? So of course, then the Jacobian is also a matrix, right? So input is a matrix, output is a scalar, then the output is a matrix, right? Because you want to know how does it affect the output. So now a bit more complicated. If you go to an output, which is a vector, okay? The output is a vector. So let's say you do something like this. F of x equals to, I don't know, x and x squared, for example, right? So input is a scalar, output is a vector. If you compute the Jacobian, what do you want to know? You want to know how does changing this input affect this component and the other component, right? So the output of the Jacobian is again a vector, right? You have a scalar in, but you want to know how does the scalar affect every of these components of the output. So it's a vector, okay? So similar, if you now have a vector in and a vector out, right? So for example, this here, let's make a simple example, right? Now you have a vector in and a vector out. What do you want to know? You want to know how does changing the first component here affect the fifth component here in the output? How does changing the third component here affect the first component here, right? You want to know how does it change in one of the components in the input affect one of the other components in the output, right? And since you have here a vector, let's say 10 components in, and here another vector, let's say 5 components out, of course what you're interested in is a 5 times 10 matrix, right? Because you have 5 in and 10 out, okay? So you have here a matrix of a specific, so you have a matrix, right? Because you have input and output, which are all interacting with each other, okay? So this is why the Jacobian in this setting is a matrix, right? It's a vector in and a vector out, so Jacobian is a matrix. But indeed, it doesn't stop here, right? It doesn't stop here because in general, this Jacobian, so to say, is can be a tensor. For example, if you think about you have a vector in and a matrix out, right? Then you want to know how does every component of this vector, let's say 10 many, affect every component of this matrix, which itself has like, I don't know, 10 times 10, a shape of 10 times 10, okay? So technically you're getting then, for example, a 3-way tensor out, okay? A tensor means, right, you have like this kind of 3D array, right? So this could be here, this variation corresponds to the input. So let's say the vector here corresponds to the input. And then you want to know what is the effect on the output, right? Which is measured then here, for example, by this matrix. You see that this is like this kind of a cross product between all these different dimensions, right? You have all these dimensions here interact with all these dimensions here. Here's the vector, so to say, and here's the matrix. Or if you have a matrix in and a matrix out, it would give you even a 4-way tensor. Okay, a 4-dimensional array, so to say. Because again, technically you are computing this cross product of interaction. How does every change here and every of these individual components affects every of the output components, okay? So back to the actual question, right? In this simple neural network, right? The simple one-layer neural network, one hidden layer neural network, which we had here, the local derivative contains this partial derivative of a with respect to w. Okay, and since a is a vector, this is a vector, and w is a matrix, what we are getting here is a 3-way tensor. Okay, so this term indeed has 3 indices, I, j, k, where I relates to the input, ai is the specific input, and jk correspond. Not input, sorry, for the output, because this is the output, and jk is the specific components of the w. Okay, so here when we are looking now at this very general form of computing the gradient, we indeed have to operate on this kind of tensors, if you really want to technically write it down, because these shapes we have here have, for example, a vector or even a matrix, and then we have here another matrix, which are the weights, and then we are technically getting here a 3-way tensor. Okay. So now back actually to this back propagation, to computing the gradient, because this was now just a tiny detour to a matrix calculus and to all these Jacobians and so on and so forth. As it turns out, at the end of the day, we don't really want to go this route. We don't want to really materialize this 3-way tensor because, as you can imagine, this can become extremely large, right? Because in practice, we have many, many different parameters. Let's say we have millions of parameters. And if we want to compute all these different kind of this cross product, right? Let's say we have here already millions of parameters and here already hundreds of dimensions, right? Then we have many, many different values to materialize, to store. Right? So we want to avoid this actually. This is not what we want, right? Or put differently, in simple terms, computing these local derivatives, which I told you before how we do this, we actually don't want to do this because it's too expensive. Here you see it one more time. So before I said computing the gradient, for example, with respect to our loss function with respect to the input x, can be written here as this product of local derivatives, which is correct, right? So we can write it as with respect to y and then y with respect to x, and then just multiply this. We actually don't want to do this because this, for example, or some of the other terms, they can become very large, okay? So we want to avoid this actually. So how can we avoid this then? How can we avoid computing this? And the full point here is, if you look again back to what we actually want to compute, we are not interested in this term here, right? We are not interested in the local derivatives at all. We are interested only in the global derivative, Okay, we are interested only in the global derivative. So really only in this one and not in this part. So the core idea is, and this is what I want to show you here, is that we want to not use these local derivatives, but we want to accumulate the gradients on the way we are calculating this. And this sounds now very complicated, what I just said. So what I mean with this is we want to, for example, not compute all these individual local derivatives here in the middle, but the core idea is that we, for example, compute a, let's call it accumulated gradient, or like a semi-global derivative, or like a part of the global derivative, meaning up to this point here. So let's say we can compute E with respect to Y, right? So this part here, right? Let's assume we can compute this somewhat efficiently. Then from this, we want to get this here, okay? So we don't compute this part, right? We don't compute really the local derivative, but we immediately aim for computing this global derivative, assuming that we would stop here, so to say, right? You see that this here is the global derivative with respect to Y, right? And it's not the local derivative as before. Okay? So this is actually now our goal, right? The goal is to somehow get an efficient way computing these global derivatives, so to say recursively, on the global derivatives we have derived until a specific part, right? So the question again, right? How can we get this one, for example, knowing, for example, this kind of global derivative? Okay. And indeed, as it turns out, this can be done rather efficiently without materializing this specific Jacobian. And let's look at this in a bit more detail, right? Remember, big picture is to compute this, but we don't want to access or materialize this one. So let's look at an example. So here I just mentioned in a big picture again before we work it out for a specific module. So this backpropagation, or this accumulation, what I just said, right, on an abstract sense should really work in the following as in two steps, right? On one hand, we have this forward pass, which we have seen before already, right? We're computing all these intermediate steps. And then we have this backward pass. And the backward pass is now not computing really these local derivatives. And at the end, we multiply them. But the backward pass is aiming to get this incoming global derivative until here, so to say. Right? You see, we compute the global derivative until here. And then what this backward pass should do, and that's our goal, is it should report the global derivative of the full chain, so to say. Okay? So this is again our wish list. This is our wish list to do this in an efficient way, right? Not the local derivatives, but the global derivatives we receive from here. And then based on this in some way, and we see it in a second, we want to get the global derivative of the full one. Because this is really what we care about, one more time, right? We care about this global derivative here, and we don't care about the local derivatives, okay? So these are the two pieces we want, right? The first one we have solved, the second one we haven't solved yet. Let's look at this, right? Let's go back to our actual problem so that you don't lose track here. So we started, and this is hopefully what you understood so far, from our goal, and we derived it by applying the standard chain rule, or now with the Jacobian, right, where we have all these local parts. And now we had our definition of, let's say, our affine layer, okay? So let's look at this. So forward pass, one more time, is really just computing the function, right? Forward pass means just evaluating the function, and then we have it, right? We have seen that already. Backward pass means we assume now for a second we can receive this global derivative. Okay, it's like some kind of a recursion. We assume we have our local derivative, our incoming global derivative up to the point A, so to say. And now again, what is our goal? We want to compute different ways. We can, for example, compute E with respect to W, or E with respect to X, or E with respect to B. Okay? Because in principle, we can take the derivative, the Jacobian, with respect to all of these with respect to all of these parameters and variables. So how can we do this now? And indeed, how it works is by first doing it in a scalar way and deriving it, so to say, by hand, right? In a symbolic way. So let's look at it in a detail. So let's say we have our e here and we have our variable we want to compute the derivative of, right? Let's say for WKL, right? This is one specific scalar component of our big W matrix here, right? And we want to get this this global derivative, okay? With respect to our A. And now it's a bit tedious, and I don't want to discuss this here in every tiny detail. Please look at this at home. You can really just now derive it, right? So here you see the standard chain rule, right, with all these local derivatives. Then you, for example, can see, okay, what is our AI, right? AI is just applying this function, right? We did this in the forward pass, so to say, this wx plus b, and then it's the e's component, right? And then you can, for example, see, okay, this b here doesn't play a role anymore, right? Because we're computing the gradient with respect to w, right? So here, w, the b disappears. So we can just do all these steps, right? This is just standard calculus, right? Because these are all mainly scalars at least, right? So you can just derive it. And at the end of the day, it turns out the solution is the gradient of e with respect to ak times xl. XL being the else dimension of x. Okay? So how does it help us, right? So now we know that E with respect to WKL is nothing than E with respect to AK times XL. So of course, what we can do now is we can again represent this in matrix form, right? This is the full potential why we introduced this. We want to represent this in matrix form. So let's check, right? So E with respect to these two indices is this solution, right? K and L. And let me directly jump to the end. I guess you can quickly see this, right? So if we have, for example, our x's, right? So all these x's stacked into one vector, right? And we have here our Jacobian, right? And what was the Jacobian again? Here, right? The Jacobian is, there's a typo in this slide, by the way. This should go up. Give me a second. This should go here, actually. So this vector here, if we take here this Jacobian or this global derivative of A, we see that here we have E with respect to A1 and E with respect to AH, right? Because this is what we assumed is given as an input. Let me scroll back to make it clear to you. Right here we assumed we have E with respect to the vector A given as input, right? So this is the vector we have as input. And then we see that this multiplying these two, right? Remember, this is a column and this is a row vector. This will simply give us a matrix, right? Because this is what is written here. So E with respect to A, K is one of these components, times XL is one of these components. So this product between this column and row vector gives us a matrix, and this matrix is exactly our derivative. And now you see what is going on, right? So this matrix here is simply also just the Jacobian, right? So this is the Jacobian we are interested in here, right? This is E with respect to W11 or E with respect to W1H, right? So simply speaking, if we really just want to write it now in matrix form, we have found our solution, right? We have found that the global gradient of E with respect to W is nothing else than X, the vector X, times the incoming global derivative from the next layer, so to say, from the next module, okay? So you see on one hand, by the way, what I said already, that this matrix form is much more efficient on modern hardware, right? We don't have for loops, we have the GPU computation. But even more important, that's the full point I want to make, we don't have to materialize this local derivative. As you see, here we have a three-way tensor. Vector, matrix means this is a three-way tensor, okay? Here, however, we don't have this. We have here a vector, x is a vector. We have here a vector, which is the incoming global gradient. And multiplying these two vectors gives us here a matrix, which is the solution we are interested in. Okay, so there is no tensor involved here, there is no big materialization, we have just these two vectors, right? One is a column and one is a row, so this gives us a matrix. Okay, so back to this big picture here. So indeed, in this backpropagation, we are not computing all these individual local gradients actually, right? What we are computing are these accumulated gradients, or these global derivatives up to a specific points. And then how it works is we have the forward pass, which is simply evaluating these modules. We are computing these values along the way, right? We are computing, so to say, y hat, we are computing h, we are computing a, and so on and so forth, whatever we need, right? And then we go backwards and we are computing these global derivatives. Okay, we are computing first e with respect to y hat, okay, which is simple because that's the last layer, we can just compute it. Then we are computing e with respect to h, okay, and we can do this very efficiently as we have seen in the other example. Then this e with respect to h is sent back to the previous layer, right? Again, it's the input to the other layer, and we compute e with respect to a, okay. Once we have computed e with respect to a, we send this to the next, or to the previous layer, right? Because we are going backward. And then we are computing e with respect to w. Okay? So this is indeed what we do. Forward pass, computing all these values. And then backward pass, computing always these global gradients e with respect to the point where we are at the moment. Right? And again, here you see it. We have e with respect to a given, right, recursively given. From the back it comes to us, right? E with respect to a is given, and from e with respect to a given, if we simply multiply with x, for example, we get e with respect to w. Okay, so you see this is very efficient and no big materialization. And as you can imagine, of course we can do the same for the other parameters, right? Because in general, if we have such a module, right, the module has three inputs, which are this matrix, this vector, and another vector. Okay, so that it has three complex inputs, this module, right? So this module has three complex inputs. One is the w, one is the x, and one is the b. Okay, so you can see like w, x, and b, they go all to the node a. Okay. So w, x, and b, they are all input to the module, so to say. They are now like evaluated, and then the output is again a vector. Okay. And then, of course, in general, if you want to implement this backpropagation, you do not only have to provide the backward step for one of the inputs. Of course, you have to provide the backward step for every possible input, right? Because you don't know at the end of the day where you want to take the gradient of, for example, right? So meaning you need the gradient with respect to w, with respect to x, and with respect to b, with respect to all the inputs you want to compute this global gradient. Okay? So we don't do this again here in detail. Please do this at home. But as it turns out, for this first derivative with respect to w, it's simply like this matrix multiplication. And the same holds for the other ones. If you want to know the gradient with respect to x, for example, it's just again the previous global gradient you are getting as input multiplied with w. But for b, it's again just the global gradient you receive as input. So you see in all these different cases, the backward step is extremely simple and extremely efficient. Okay? And indeed, this is what you then have to provide if you want to implement this by hand, so to say. If you want to implement a module for backpropagation by hand, you have to provide these two functions. You have to provide the function forward, which is really straightforward because it's just the function you apply. And again, here you see the three parameters which go in, three variables which go in. And you compute the output, so to say, of this function. And then you have to implement a backward function which receives the global gradient from your output, so to say, right? From the next layer, right? So this module you have receives the global gradient from what comes next, so to say, right? And then what you have to implement are these accumulated gradients, the global gradients, in this kind of recursive fashion, right? So you have to derive what is this based on what you have received and based on what you have available at the moment, right? And as you can imagine, you can always do this, right? It's not that you cannot do it, it's always possible to do this. So once you receive this accumulated global gradient from the later layers, you can always write down your own global gradients in a specific way. But of course, it requires some work to derive it, okay? And now we have it, right? Now we have all we need, right? And here it's again just a big summary. So what you have to do to do backpropagation or to do learning in a neural network is the following. First, you define this computation graph where you have these different modules. Okay, you have the different modules. And the modules can be very simple. They can be these affine layers. They can be more complicated layers. They can just be also like variables. Like here, for example, W is just a matrix. This is also one specific module, for example, right? Which is just a variable, for example. So you have these different kind of modules. And what you have to provide for every module is the forward pass, which computes simply the output, and you have to implement the backward pass, which accumulates the total gradient. Okay, it gets the gradient, the global gradient from the later layers, from the later modules, and it accumulates it. And then the output, right? The output of this function are these three matrices or vectors, right? And these would be then sent again, of course, to the another layer from before, right? So here we have, for example, another function b here, right? So this function here, for example, has a forward function, which produces the output, and has a backward function, right? And this backward function is e with respect to b, let's say, right? And it sends it here to a, right? And a receives this as input to its own backward function, computes its own backward function, sends it the result to the next step, so to say, right? So the output of this, of A's backward function, which are these three matrices, are sent here, here, and here. Because these can, of course, also be somewhere a result from something else, right? You have to imagine that these are modules in your so-called computation graph, okay? So forward step sends the output to the next layer, and backward step sends it to the previous layer. And this is also called why it's forward and backward, okay? So long story short, you have to provide these two functions, okay? And once we have these functions, right, we get our gradient in a very efficient way. Again, for two reasons. First of all, we do not really write down the full gradient of the full function. We just evaluate the gradient at the current point, which we need for gradient descent. I compute the gradient at the current parameter solution. Okay, this is why we do this forward pass. Okay, and second of all, why is it so efficient? Because we do not really materialize the Jacobian, because we do this recursive backward step where we can rely on the previous results, on the previous global gradients we have already computed, right? We have this recursive calculation, so to say, right? And this makes it also very efficient, okay? And lastly, since we often just represent it in matrix and vector form, this is super fast to implement on a GPU. And then, right, finally, what I said a couple of times, so backpropagation essentially works through this computation graph in actually twice, right? First forward and then backward. And so we have to visit every neuron, every component, every module only twice, which makes it extremely fast. So before I wrap up here or conclude, just again, some points which you should be careful with, right? So please don't confuse these computation graphs with this neural network illustration I've shown you at the very beginning. In the very beginning, the weights were attached to these edges and they had specific meaning with these affine or linear operations and so on and so forth. Here in this view, this is called a computation graph or computational graph. Here it has a different meaning. You see, for example, that the weights and whatever these x's and b's are, these are always in nodes, okay? And every data object, let it be like the input X or let it be the weights, every of these matrices and vectors corresponds to one node here, right? And here you don't really see the operation, because this A, right, this A is the operation, so to say, right? So A means we're taking W, multiplying it with X and adding B. Okay, so here this node represents the operation as well as the output. Okay, so you can, for example, imagine that this is like doing like input 1, right? Input 1 times input 2 plus input 3, right? So this is what this module is doing. Input 1 times input 2 plus input 3, okay? So this is how you can imagine this, and this is then what the corresponding output is. And this is known as a computation graph, as I said, and this is what you see in all these modern deep learning frameworks, how it's used. Okay, and with this actually, we have all the pieces ready, right? So now you know what in general a neural network is, right? It's just a hierarchy, a stacking of different functions, of nonlinear functions specifically, right? And they allow you to also, for example, classify nonlinear separable data. And intuitively, it means we have like learnable basis transformations of our data, right? And we usually do it in a deep sense, because then we have lots of expressive power with hopefully also a few parameters, right? And what we then need to train this neural network is we need some kind of loss function, and we need then gradient descent to minimize this loss function. And to apply gradient descent, one more time, we need, of course, to compute the gradient, right? Because that's our gradient update step. And how do we compute the gradient efficiently? We use backpropagation, okay? And backpropagation in the modern sense is essentially composed of these different modules, right? And these modules have this forward and backward functions. And once you have these two functions implemented for these modules, you have your plug and play component. You have your Lego, so to say, right? Because you can stack these modules together how you want it, right? As I said here. So this module is computing input 1 times input 2 plus input 3, right? And once you have implemented this module, once you have implemented these two functions, so to say, you can use it in various components, right? You can use it here, and you can again, for example, have another setting, right, where you have here now, let's say it continues. So we have here another A used, for example, I would call it A prime now, which gets this as input and two other inputs, and you continue, right? So once you have these modules implemented, you can use them in various pieces in your neural network architecture. It's just reusable. And again, this is the full power of these neural networks, and this is the nice advantage of all these modern deep learning frameworks. They have all these different modules available. Of course, you can implement your own, but they have many, many different modules available. They have these modules for these fully connected layers, and many other modules we will very quickly talk about also in other videos. But in general, you have these different components. You can plug them together. You can specify, again, which loss you want to use. Be careful what kind of last layer you're using for your task, right? Because the last layer usually determines what is your actual machine learning task. Is it binary classification, general multi-label? Is it a regression scenario whatsoever, right? So the last layer is the most important one for that. But the rest is extremely flexible. You can just exchange it. And as said, it's very efficient to implement via backpropagation. So with this, I guess we are at the end of this first part of neural networks. As usual, feel free to ask your questions online. Otherwise, in the next videos, we talk about specific learning strategies, specific problems also of neural networks and how to encounter these. And as I said already, a few specialized architectures to see that it's not just like this fully connected multi-layer perceptron where we're always doing these affine layers and the nonlinearity, but there are some special modules, so to say, available. So thanks for your attention, and we will see us in the next video. Bye bye.